Okay, cool. Yes, so welcome to lecture 9. As I say, we're going to talk about sets and relations. The plan is to start off by spelling out some basic set theory. Now, I want to stress the motivation here is to introduce and familiarize you with some notation and some concepts. This is definitely not a mathematics course. This isn't a set theory course, anything like that. My aim here is to basically make you familiar with this sort of ideas, so when you come across it later in life, in some future studies, you'll be like, oh, I know what the hell these little squiggly brackets mean, and I know what a transitive relation is, and things like this. That's the aim for this lecture. So we'll start off with basic set theory. I'll highlight the things that we absolutely need to know, that'll be relevant for the exam and such. I'll also give you a bunch of other stuff too, but again, don't panic, right? This is just cool stuff that's worth knowing. Then we'll talk about Russell's paradox, which is a paradox for a particular conception of set theory. And then we'll talk about the nature of relations. And here again, it's me trying to familiarize you with certain definitions and concepts. I'm going to give you a whole slew of them, but I promise that I will highlight the ones that I will possibly ask you about. Right? So it's not just going to be, hey, here's 30 definitions, good luck, ha 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 ha. No, it'll be, here's the 4 or 5 that actually we're going to talk about. Then if we have time at the very end, we'll talk about some fun stuff, Hilbert's Hotel and infinite sets. So that's the plan. Let's rock and roll. So the idea of set theory. We can get the idea of set theory going by first thinking about how to approach collections of entities. So we can think about the people who are in this class or the people who are in this room and think about that collection versus the group of us. So for example, the collection has an even or an odd number. Right? Depends on how many of us there are. Right? An even or odd number of members, say, things that make it up. But of course, you could also say there's only one collection. It is this group. Same thing too, we think about the people who live in my house. Right? We can think about that as a group, or we can think about the 3 constituent parts, Mira, my dog, Amanda, and myself. Now, notably, if we think about the individuals, well, we're thinking about these specific individuals. Maybe we're kind of thinking about them in conjunction, but it's still about those people. But we might also want to talk about the group itself. The group itself has 3 parts, Nathan, Amanda, and Mira. Notably, none of us are made up of 3 parts, at least not in that same way. Again, so the thought here, that I'm trying to get at, this intuitive thought, is that whenever you have a collection of entities, there's a distinct thing that is the collection itself. The collection can be thought of as something over and above the mere objects that are in it. The things make up the collection, but the collection is not just these things. Again, that's a kind of intuitive thought. We don't necessarily have to buy it. But something like this thought underlies set theory. Set theory in particular formalizes this thought in a very rigorous way. More importantly, set theory is everywhere in mathematics, in linguistics, in formal semantics. And that's because what it lets you do is treat collections as yet more mathematical objects.
So could you explain the third point?
Yes. So the idea here is that we don't just want to say a collection is merely reducible to the things that make it up. We can talk about the collection as a separate and distinct thing that has the parts that make it up, but it's something extra. So there is the collection that is people registered for this class, and then there's you, etc., 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 etc. And we think about these as two different things. That list, those are all the people who are in the collection. But the collection is not reducible to, in some sense, just that list.
Is the collection reducible to all the things that could be in the collection?
So importantly, not when we formalize it. So we'll have multiple ways to kind of pack out this idea. The way we're going to get it is actually not going to allow for change in membership. And we'll see why in about 3 slides. Right? But this is just one particular way to start thinking about the relationship between parts and something like collections. This is just one approach, and set theory gives us a really rigorous way to cash that idea out. Yeah?
So in a nutshell, the collection is more than what's...
That's the thought. Or at least it's something extra, right? It's a thing itself, not just the parts that make it up, not just these little elements. Yeah. That's what really I'm after with this something over and above. Another way to put it, in the vernacular we were talking about last week, is if we kind of flesh out the commitments of this idea, the ontological commitments, we'll have all the individuals and it will have collections. So its commitment isn't just to Mira, Amanda, and Nathan, it will also have a fourth thing, the collection that has Mira, Amanda, and Nathan as parts of it. That's the kind of intuitive idea. Again, I think it'll kind of come out as we think more about this general approach. So let's introduce some terminology. A set is a collection of things considered as a whole. So the set is the collection. If you want to think about it this way, you can think about it as a box or a bin with a bunch of stuff in it. And when we think about the set, we're thinking about the bin and whatever's inside it. So that's a set. Members are the things that are collected into the set. They are also called elements. So, to go back a slide, right? If we think about the set of people who live in my house, Mira, Amanda, and I are members of that set. We're part of that collection. And then just to mark a difference, we can talk about individuals, or if we're being fancy, elementa. These are things that aren't sets. People, tables, chairs, houses, most things. Just non-sets.
Is a set the same thing as a collection?
Good. So, yeah, basically. Importantly, this definition doesn't force us to say that every collection is going to be a set. But we can think about sets as just this separate kind of object that's very specifically understood as a collection.
How about collections that only have one thing in it and couldn't have more than one and couldn't have less than one thing?
That's perfectly fine. We're going to actually give you a term to talk about those. We're going to call those singletons. Right? That's not even the minimum collection. The minimum collection is the empty box, the null set. More on that in a second. Okay, so again, 3 basic things. You've got sets, you've got individuals, and then individuals can be members of sets. They can be parts of the collection. We express this using the membership relation. The membership relation is symbolized with this thing. It looks a little bit like the euro symbol. Right? And this is to say that the thing on the left is a member of the set on the right. This is a relation that holds between a member, an element, and a set. Now again, let me stress, the things that can be on the left can be individuals. They can also be other sets, because sets are objects too. But the thing on the right always, 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 always has to be a set. You gotta be a group. So this tells us Mira is a member of the set of dogs that live with me. Notably, Mira is not a member of the set of people in this room, because that would probably lead to a biting incident, and we don't want that. Now, the way we write sets down, we can write out a set by writing these squiggly little brackets, and then we just list the things that are inside the bucket, list the things that are in the collection. So Mira is a member of this set that has her and Darth Vader as members. Nathan is not a member of that set. I'm not in that box. I'm not in that bucket. So again, membership means to be one of that group, be in the group, be an element in the set. So this is one of the fundamental relations for set theory, membership, to be a part of it, to be an element of a collection. Now, importantly, using membership, we can individuate sets. So we will say that two sets, S and T, are identical if and only if they have all and only the same members. So I've written it out in FOL. This tells us that two sets are identical if and only if everything that's a member of S is also a member of T, and vice versa. So this is the axiom of extensionality. It gives us identity criteria for sets. When are they identical? Well, they're identical if they have the exact same members. So when are they different? They're different if they have different members. So this is the reason why we're not going to allow for members to change over time. Because if we have changing over time, we lose identity of the set. Again, it's just one way to kind of cash this out. Yeah.
So how about two sets that have different criteria but contain exactly the same?
If they have exactly the same things, they are the same collection. Again, this is it. So this is why it's also called an axiom of extensionality. Right? We've seen this word before. Do we remember where extension was? So probably some nightmares coming up, right? Yeah, right? The extensions of a predicate were the things that satisfy it. Here's something really cool. We were actually doing set theory when we were building extensions. Right? We were defining up sets. We just did it without the squiggly brackets because it's confusing enough already. Some really cool things to note. One thing, order of presentation doesn't matter. These two sets are the same. The set with Socrates and Plato as members is identical to the set with Plato and Socrates as members. Again, you can think about it as basically just a bucket. We don't care how you packed the bucket, we only care what's in it. Similarly, repetition of names or different ways of referring to the same object don't matter. These two sets are identical. Because these are just two different names for Superman. So if you open up this box and look inside, you're just going to find the one object. And this is also another name. This was his Kryptonian name. So this is also just, if you open it up, find the same dude. So two lessons here, right? Order of presentation doesn't matter when we're just thinking about sets. All that matters is what's in there. And the number of different ways you refer to objects doesn't matter. All that matters is what's in there. Okay. Now, some further notation. Right? We can write, again, we write the set with these curly brackets. We can use this to basically say the set of all things X that satisfies some condition. So for example, down here we have the set of all things that satisfy the predicate H. H could be, is a happy thing, or, I don't know, is a harrier, doesn't really matter. Is a Hollander, doesn't matter. Yes?
I don't really understand that.
Good. So basically, set theorists are kind of lazy. If they write just a variable like this, there's a hidden universal quantifier there. So this is basically saying everything that satisfies some FOL sentence. So everything that's an H, everything that's such, if it's an F, then it's a G. Da 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 da.
Oh, so it's just universal quantifier.
That is. It's a universal quantifier and then saying, hey, and you make this sentence true. That's all. It's just a cheap and cheery way to write that down. Yeah. Okay. So again, the core idea, you have these collections, right? And if you're in the collection, if you're in the squiggly brackets, then you're a member of that collection. You stand in that thing that looks like the euro sign. So membership is one of the two fundamental relations. The other fundamental relation, one more slide about membership. First thing to note, individuals can stand in the membership relation to sets. So Socrates is a member of the set with Cicero and Socrates as members. Nothing ever stands in the membership relation to individuals because they're not collections, at least not as we're understanding them. But importantly, sets can also stand in the membership relation to other sets. So take this set with Socrates and Batman as members. This collection is a member of this big collection over here. In fact, if we look at this collection over here, the big one, it has two members. It only has two members. Its two members are this collection and this collection. So here's the thought. When you open up the big box, you look in and you see two boxes, and you don't look inside them. You just say, cool, there's an object, there's an object. Don't care if there's stuff inside it. So basically, you could just say, hey, over here you've got box A and box B. And that's what's in this thing. And then this is box A, and that's why it's a member of the big set over here. Again, that's kind of tricksy. But if we get this, you've got everything I really want you to know about the set theory stuff. So, is Socrates a member of this set?
Yes.
Yeah, he's a member of that set, right? Is Socrates a member of a big set over here? No, he is not. Because the only things that are members of this big set are two collections. Now, he might be a member of one of those two collections, but that don't mean he's in the big group. Here's a way to think about it. Are you a member of TSHD's collection of departments? You're a member of the philosophy department. Cool. Are you a member of TSHD School, which is a collection of departments? Not strictly, because it's a collection of departments. Unless you yourself is a department, you best not be in there. That's the idea here. Do we see the thought? Do we see the thought? Again, another way to think about it, right? Are you in my collection of tutorial groups? Well, we could talk about that kind of fast and loosely, but you are not a tutorial group, right? You are a person who is in one of those tutorial groups. Yeah.
So with the example of the TSHD department, the only members are the departments.
Are the departments.
And we are only members of the department.
Of the departments, exactly.
And that's how you need to look at it. That Socrates and Batman is one.
Yeah. So they're parts of this collection, and then that collection is part of the bigger one. But that does not mean that Socrates and Batman are parts of the bigger set. They're not members. They're packed away in that box, and then that box is packed in the bigger box.
So it's not lining up, but from the top.
Now, we could build a set that Socrates is a member of. So, for example, let's take the big set over here. We've got Socrates and Batman. And then let's just add Socrates. Now, this one, how many members does this big set have? It's got 2. Right? One of them is a dude, and the other is a collection. Now, importantly, inside this collection, if you opened it up, you'd find Socrates again. But we don't do that if we're just counting who's a member of the big group. Yes?
But like Socrates in his alone could also be in the box.
Yeah, that could be totally fine, right? So another set we could build. How many members does this set have? It's got 2. It's got your man.
Oh, the difference is the bracket. Oh.
This is why I want to teach you the notation.
Because if you put a bracket in front of the second S,
Then
then
Socrates.
it's two boxes. Then he's still not in the.
Come back to that. Yeah. So right, so far, this thing's got 2 parts, right? It's got the collection, and hey, he's in here. But he's in there, right? All we care about is that it's thinking about the box. So the members of this set are this box and this dude. But, oh, he's also in that box, but we don't care. Now, let's go back, think about your question. So obviously, right, the brackets tell us we've got a set. So if I do this, how many members does this big set have? 1.
Oh.
Because it's the same package twice, right? It's just like Clark Kent Superman. Right? Repetition of the object, repetition of naming the object, don't mean it's in there twice. If you open up this box, you're only going to see one other box. You just happen to call it twice. Yes?
But does adding the extra bracket make it 2 individuals instead of one collection, one individual?
Good. So, when we did this, when I added those brackets, that was what made the change. Because adding those brackets, that meant I'm no longer talking about Socrates. I want to talk about the collection that has
adding
Socrates.
brackets make it-
So that now is one big box.
This is one big box, and all that's in it is that. Named twice.
Are those individuals or members?
Good. So, the only individual that we got here is your man Socrates, right? Because individuals are things that are not sets. So, if we're ever talking about an object that's got the brackets around it, it ain't an individual, it is a set. They are members because they're a member of that collection. Again, the idea with being a member is you are part of the collection. You're in the box. And the things that can be in the box could be individuals, stuff that isn't sets, or sets.
So does that thing now have 2 members which are the same thing or 1 member?
1 member. This only has 1 member. It's got this same box listed twice.
But what if like you have Socrates Batman and then Socrates Batman Cicero Superman? But if that would be like Aristotle and Nietzsche and Superman and Iron Man.
Then we got different sets, right?
But it's still the same
Good.
thing.
So remember, the individuation is about having the same members. So if, for example, you got Socrates, Batman, and Nietzsche, and then you've got Socrates and Batman, looking at this big set, How many members does this big set have? It's got 2. It's got 2. It's got 2 because one collection is this one, and the other collection is this one. Now, they happen to share some members, but they don't have entirely the same members, so they must be different sets. We'll work through this. We got a worksheet that we'll talk about on Friday. But again, this is the general idea. So, that's membership. Okay? An interesting question we'll come back to. Can a set be a member of itself? Let that percolate in the back of your mind. We're going to talk about it in a few minutes. The other big relation that defines set theory is being a subset. Now, membership we wrote with that symbol that looks like the European, like the euro sign. Right? Subsethood we expressed with this symbol. Now, what does that look a hell of a lot like? Less than or equal to. Less than or equal to. Yeah, exactly. And that's the concept. That is the idea. So S is a subset of T if and only if everyone who's a member of S is a member of T. Right? Put another way, S is a subset of T if everybody who's in the group S is also in the group T. T could be bigger. It might have more people. Or it might be the same damn set. That's what it means to be less than or equal to. So again, subsethood is a relationship between collections. Always and only between sets, between collections. You cannot have an individual be a subset of a set. Doesn't make sense. Because you're not in the set game, so you don't have no members. So you can't have everyone who's a member of me is also a member of this. Nobody's a member of me. Yeah.
But every citizen of Tilburg is a citizen of the Netherlands?
That's fine, right? That is to say, right, that everyone who's a member of Tilburg is also a member of the set Netherlands. And in turn, that means being a citizen of Tilburg is a subset of citizen of the Netherlands. Right? Because everyone who's in the first set is also in the second.
But it's not that I am a citizen of Tilburg, so I'm also a citizen of the Netherlands because I'm
That's fine, right? Again, so there's a relationship that we can talk about if this first set is a subset of the second one, you have to be members of both. Right? Because again, to be a subset means everyone who's in the first is also in the second. Now, again, subsethood is this less than or equal to sign. But you might be interested in something that's strictly smaller. And so that we have the notion of proper subset. Proper subset just means literally smaller than. It has to be smaller. So it just drops the or equal to. And we can define being a proper subset. So note, we used just this little horseshoe without the bar underneath it to avoid the equal to. It just means is less than. And we can define it as, hey, S is a proper subset of T if and only if everybody who's in S is in T and they're not identical. And this forces T to have more members. Okay. So again, the important thing for us here is this concept, right? The notion of being a subset. Yes?
So, isn't the thing below the definition of a proper subset?
That's what this one is, yeah.
Okay, yes.
Yeah. But the one in the big blue box is for being a subset.
I was reading.
So again, subsethood is a relation between collections. Membership is a relation between individuals or collections to collections. Yes.
How can if two sets are the same thing? How can they be a subset of each other?
Good. So the important idea here is that, again, subsethood is less than or equal to.
Yes, but if it's the same thing.
Then they're equal to. That's the idea, right? So again, subset is just less than or equal to. So again, the weird edge case is when they're equal. Yes, sorry, we'll come back to you.
So definition below should say proper subset.
Yeah, so this one
That's
down
a
here.
subset of T. But that's-
Yeah. Yes, this is a proper subset. So this should be the same thing. Yeah, sorry, that's what you were after. That was my mistake. Yeah, it's a typo.
So a subset is just could also just be the set again, but we'll just call it a subset for convenience.
There you go.
Or for disconvenience, actually.
Well, so it's useful because one of the things that we can do once we have this idea of less than or equal to is you can define what it is to be just strictly less than. It's very hard to go the other way.
So if it's equal, if two sets are equal, they're also identical.
Because remember, equal is just a handy way, much like with FOL, right? It doesn't actually say equal, it says is identical to. So this is a sentence of kind of extended first order logic. The only thing we're adding is some of these set theoretic notations. Okay, so again, we've got being a member, that's to be in the group. We've got being a subset, which is to be a smaller group, less than or equal to. Now, here are a few things. Every proper subset is obviously a subset. Everything that's less than is less than or equal to. But obviously not the other way around. And notably, two sets are identical if and only if they're subsets of each other.
Individuals cannot be in the first part, on the left side, right?
Mhm. Again, in fact, in this case, individuals can't be on either side.
Yeah.
Whenever we're thinking about subsethood or proper subsethood, it's always got to be sets on both sides. Because it's a comparison between the number of members, who are your members. And if you don't have any members, well, you don't get to play this game.
So it's only about the members within. So you could say on the below one, you could say Socrates, or does it have to be a member of a set Socrates on the other side?
Good. So it's always got to be sets on both sides of these relations, right? So if you just had Socrates, well, you can't put the subsethood or proper subsethood relation here. It's the wrong thing. Because the only kind of things that you can put this relation that it actually attaches to need to have our squiggly brackets. Okay. So again, I just really want to get you the basic concepts here, get you the notation. This is the kind of thing that you might run into later, and I want you to be familiar, at least a little rough and ready with it. Now, on the flip side, right, if being a subset is to be less than or equal to, well, we can also define the other way around. A superset is greater than or equal to. It's just the other way. Right? S is a superset of T if and only if T is a subset of S. Again, think about it this way, right? If subset is just less than or equal to, superset is greater than or equal to. All we need is just one of the two. And the core idea is just this idea of comparing members, right? A superset is just a flip. It's bigger.
Is it possible that you have like a set of things where there can be a superset above it anymore? Already everything.
If we have the time, we'll get to it when we think about the infinite sets. That's a kind of fun one. Right. Okay. So again, the core things I really want you to get, the membership stuff and the subsethood relation, and get the difference between these relations, right? So being a subset does not mean that you're a member. Being a member does not mean you're a subset. Because being a member is to be part of the group. And some of the things that could be part of groups are individuals, and individuals are never subsets. But you could have both. Right? In fact, for an example of both, so let's rock and roll. A few more terms. I'm going to throw some stuff at you. Again, there's a lot. I'm going to try and highlight the stuff that you have to know. This is stuff I think it's worth knowing. So you mentioned sets with just one member. We have a term for that. We can call them unit sets or singletons. These are collections with just one object. The smallest set there is, however, is the empty set, the null set. We write it with this, I often write it with this 0 with a line through it. This is the set that has no members. It is an empty box. The null set is the number of people who love you. Oh. Or, well, if the recording wasn't going, I'll say it. It's the number of fucks given, right? None. But notably, the empty set is still a collection, right? It is just a collection that has no members. I know, it's weird. So the empty set is something that's postulated to make a lot of this machinery work nicer. Without it, some things get really messy, which, trust me, it's already messy. So the empty set's cool. The empty set's cool because it is a subset of every set. It is a subcollection of every set at all. And here's the reason why, right? So let's plug in the empty set as set S, and any set you want as T. Well, because it's the empty set, the antecedent of this conditional is false. And what's the truth value of a conditional with a false antecedent? It's always true. So it's always true, no matter what set T is. So the empty set becomes a subset on the cheap. That's what this block here goes through that reason. Notably, the empty set being a subset does not mean that it is a member. Right? It's a smaller collection, but that doesn't mean it is part of every collection. Again, the stress point, membership and subsethood are different relations. Please.
But is the empty set member or something?
Yeah, it can be. So for example, it is a member of the set I have here. Right? So it's that member, and then you have Socrates as the other member. So in this case, the empty set is both a member and a subset of this collection.
Why would you edit?
I mean, you just might want to use it for various things. So we'll talk, if we get to it, maybe one particular application. But again, it's just kind of something to make the machinery work a little better. It's very much like positing the number 0. It's slightly strange, but actually the mathematics works a hell of a lot better once we have 0 in there. It's very similar to that. Yeah.
Is it also equal to another set?
It is. What set's it equal to? Itself. That's always the case, right? So again, remember the rule for telling when sets are identical. They have all and only the same members. So the only thing that has all the same members as the null set is the null set. Nice. Okay. So the last big thing I want to get through on set theory is to talk about 3 operations we can perform using sets. So the first operation is to get the union. Right? The union of 2 sets is the collection of all the members in both. What I mean by that is, you're in the union if you're a member of A or a member of B. So we express the union operation with this. It looks like a U, but it's actually written slightly differently. It's just kind of come through that on the slides. Union is, again, U. It looks very much like the OR symbol, the vel, the disjunction. And it's the same operation. You're in the union if you're a member of A or a member of B. So the union of George and John, John and Paul, is John, George, and Paul. Because it's basically, hey, are you a member of either one? Then you're in the union.
So you combine all the members.
All the members. That's it. It's the easiest one. It's just, hey, are you in the diagram at all? Then you're a member of the union. Okay? So union is, hey, are you in either? The next operation is intersection. Intersection is, are you in both? We express it using this. Note what it looks like. It looks a hell of a lot like conjunction, because it behaves the same. To be in the intersection of A and B, you need to be in A and in B.
Is this still FML, or is it something?
So this is basic set theory, right?
Okay.
Yeah. So it's a different kind of machinery, but it's very closely related to first order logic. It's a kind of extension of FOL.
So it's kind of a new language.
In some really loose sense, right? Honestly, one of the things that we were doing when we were thinking about interpretations, often we were playing around with things like this in the background. We just didn't make it explicit. Yes?
Could you also have an intersection of like 3 or more sets?
Absolutely. Right? So what you would do for that is you would think about the intersection from the first one, the intersection from the second pair, and then do the intersection of those 2 pairs. So it only ever takes 2 at a time, but you could just run it multiple times to kind of get, okay, I've got 4 circles, so I'll do these 2 and those 2, and then do the union, or the intersection, their intersection. Beautiful. So again, union, you're in the union if you're in the OR, A or B. You're in the intersection if you're in A and B. The last operation is difference. And the idea of difference is effectively remainder. You're in the difference of A/B if and only if you're a member of A and not a member of B. So to get this, what we do, right, is you figure out what's the overlap, who's in both, and you take that out and see who's left.
It's only left to right.
Yeah. So this is the only one that order matters for, right?
Can always also be the other way.
Yeah, but we would write it the other way, right? So we have the difference of S/T. We can also do the difference of T/S. Right? So union doesn't matter what order you write the sets in, right? It can be A, union B, B, union A, doesn't matter. Intersection, order doesn't matter. A, union B, B, union A. Difference, it matters. It matters because who's getting left? Which remainder are you looking at?
Because Paul disappears.
Paul disappears because he doesn't matter, right? So if we look at our first example, right, with you've got the set George and John, and you want to remove or remove the overlap here, which is just John. So all you're left with is the set with just George as a member. Yes.
Why not Paul?
Good. So importantly, it's always left to right. So we're doing the difference of this one once we take away the other. So if we wanted to get Paul, right, if we asked what's the difference of John, Paul / George, John, well, that's going to be this set with just Paul as a member.
Yeah, exactly. It's just because John is the same as George is.
So again, it depends on which one you're doing, right? Is it the difference of the one on the left from the one on the right? Or is it the difference of the one on the right from the one on the left? Yes.
Do you use a slash or backslash?
Good. So backslash is fine. If you do slash, that's okay too. Right? I'll always write it with backslash. But again, all that matters is right, it's the difference of the one on the left from the one on the right. It's the remainder from the one on the left, right, after you've taken away the intersection. That's all that matters. I don't care which way you do the slash. Okay, cool. Those are the three operations. So here's what I'm going to do. When we get around to the final exam, I'll give you some sets, and I will ask you to do some of the operations on them. I might say like, hey, tell me the union of these sets. Tell me their intersection. What's the difference of this one from that one? It's very straightforward. Again, this is just to kind of help you think about these things a little bit, to familiarize you with some of these ideas. Not because I want you to become little set theorists, far from it, but because I think these are operations that underlie a lot of mathematics, a lot of computer science, and a lot, actually, of philosophy of language. So it's helpful to know this stuff. Okay. So I have a few more concepts I want to talk through. One more operation. This isn't like union or intersection or difference. This you only feed in a single set. And this is the power set operation. So it's this weird, slightly sexy, swashy P. Oh, God, no. Sorry. That was a bad thing to say on the recording. So the power set function, when you feed in a set, gives you the set of all subsets. So the power set of something is the collection of all subcollections. It's basically, hey, if you were to take the stuff that's in this box, how many different ways could you repackage it? Right? What subcollections are there? Now, here's something neat about power sets. Whenever you're building a power set, one member you know will always be there is the null set. Because the null set is a subset of every set. So you know the null set's going to be a member of every power set. The other one that's always going to be in there is the set itself, the one that you fed into the machinery. And the reason for that is because, remember, it's all the set of subsets. So it's everything that's less than or equal to. And the set you fed in is equal to itself. So here's, again, we get the basic idea? So let's go ahead.
So a power set is all the possibilities of a subset.
Yeah. It's basically all the subsets that you could make from whatever you feed in, right? It's the collection of all the different ways you could repackage this stuff. Hey, I could leave it out and just leave you an empty box. I could just put A, I could just put B, or I could put A and B back in. So it's the collection. Power set always gives you a collection of sub-collections.
So this can also be infinite.
Theoretically, right? If you have a set that has infinite members, you will have a big power set.
This is the same with like this we do A, B, C. letter stop, can you put like one?
Absolutely, right? Yeah. So this is just kind of some examples, right? We could have names. You could have TFL atomic sentences, which of course there could be an infinite number of those. No problem. Right? You can put anything you want in between the squiggly brackets. That's all we need.
So what are operations exactly?
Good. So they're basically functions that we're applying to sets. So for example, when we think about the union, this is saying, hey, I'm giving you two sets, perform this function on it. It's a bit like, hey, do some multiplication with these two numbers. Or something like that. Right? And the same thing with these other. There are various functions that we're applying.
Will the second one be a bonus question in the end?
There will be. Okay. So the last thing I want to mention for sets, no, don't worry, this is easy, is about cardinality. And cardinality is the simplest idea in the world. The cardinality of a set is the number of members it has. Scary. So what's the cardinality of the null set? Well, let's think. How many members does the null set have? 0. Right? Cardinality of the null set's 0. What's the cardinality of singleton Socrates? 1. What's the cardinality of the power set of singleton Socrates? 2. Empty set and the set itself. Not a trick at all. So, cool. Basically, this is what I want to get to, right? This is the stuff I wanted to get through with regards to set theory. There's a whole slew of other stuff here, right? About how to do pure sets, things like this. We're not going to talk about it. It's okay. I'm happy with what we covered. Yes?
Cardinality of, if you put brackets over the Socrates, is it 0?
Good. So if we put brackets in here,
Yeah.
right? So, or basically, we just added an extra pair of brackets on the outside. Good question. What's the cardinality of that set?
1.
It's still 1. What is it? What's its member?
The singleton set of Socrates.
It's the singleton Socrates, right? It is the set whose sole member is a set with Socrates as a member. It's a very weird collection, but hey, people like weird collections. It's a box in a box. In fact, what we could do, so this is something we're not going to talk about, but if you start with the null set, you can construct an infinite number of sets by just adding brackets on the outside. But every time you do it, you only ever get a set with one member. So you start with the null set. Start with the null set. Throw some brackets around it. How many members does this set have? Just one. Right? The only thing that's in this box is that empty box. Then, how many members does that set have?
1.
Still just one. You can see the process here.
Why can't you do this with Socrates?
You could, totally could, right? We could start with Socrates, box him up, box that box, and so on 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 and so on. The neat thing is, that process I just gave you there, we generated infinity from nothing.
Whoa.
Do you see what we mean, right?
Yeah.
Because this process can keep going on. So we're going to have an infinite number of sets with only one member at each layer, but they all started from the set with nothing inside it.
And if you put it, I got a 60p in front of it.
Yeah, good. So if we do the power set of this, how many members is this thing going to have?
2.
2. It's going to have not nothing. The empty set and the thing that we started with, right? That's it. That's it. Very cool. Now, again, I'm playing mostly with some weird kind of jokey cases. But this machinery is so incredibly powerful from actually very, very few operations, very few ideas. Membership, subsethood, and the squiggly bracket stuff. We've just got a really powerful system for formalizing things. Honestly, what we can do now is we can pretty much get all of mathematics from this. From squiggly ass brackets on a whiteboard. Yeah, well, he loved this stuff too.
Sorry, why is that 2?
Good.
Why are there 2?
So when we think about the power set of this, it's going to be the collection of all subcollections. And that's going to be the null set, because it's a subset of every set, and the set that we started with.
Oh, so the P counts, so the power set counts as a set too.
It always gives you one, right? It's generating, hey, tell me all the ways you could repack this. And the ways you could repack this are, hey, the way you've done it, because it's only got one thing in it. Or I could take that one thing out and leave you with an empty box.
And how could you use it with like an English sentence?
So this isn't doing the same kind of work as things like FOL, right? This is more of just a way for us to think about the relationship between members and collections. So one of the things that this lets us do is start talking about numbers. We can just treat numbers as particular sets, and we can talk about all the numbers. That's just the set. So all the numbers, we'll just call it the set named Steve. Right? Steve has a lot of members. Steve is not a number. Right? These kinds of things.
But does that make all sets infinite that you can make?
No, right? Again, let's think about the null set. It's pretty finite. It's just an empty box.
Yeah.
But it's easy for us to start constructing infinities or mapping them because we have these beautiful, very simple and elegant tools.
Can you put like an open bracket around it? So that you can because
We never want to have just one of our squiggly brackets. They always come in pairs. Because otherwise, it's just kind of misfiring the system. Okay. So that's the stuff I wanted to cover with regards to set theory. Right? Again, there's more stuff in the slides. If you're interested, feel free to look at them. I'm going to skip through them, but I'm skipping through them. Right? We're not going to talk about them. I'm not going to examine you on it, anything like that. I want to get to this. So one other big part that we can talk about here, and once we have the set theory, it's very easy to do, is we can understand the notion of a function. So a function is a mapping. A function is a mapping from one set to another. And we can have lots of different kinds of functions. In particular, you can have many one functions, which takes multiple objects from one set and maps them onto a single object in another set. So for example, let's think about grades. You could have multiple students all mapped to the same score. Or you could have it the other way around too, right? If you've ever been kicked off a flight for overbooking, that is an instance of multiple people being mapped to the same seat. Very fucking annoying. But another really useful function is an isomorphic function. So you will probably come across this word in other places. An isomorphic function is a function that maps things one to one, and it preserves whatever structure there is. So here's an easy way to get it. Think of any good map. A good map is an isomorphic function from reality to representational things on the map. Right? So there's a 1-1 mapping, haha. But also, the map is only going to be good if it preserves structure. That is, the distance on the map is scalable to the actual distance between the things in real life. The structure that is in reality is preserved in the mapping. Yes?
I don't really get both of that.
Good. So a many one function is literally just, hey, we can have a bunch of objects in the first group, and we'll all link them to one object in the second. So again, we can have a bunch of people in the class, and they're all going to be mapped to the same grade. You get a 7, and you get a 7, and you get a 7, and you get a 7. A bunch of people in the collection get mapped to the score 7.
Do you maybe have an example in the object language?
Sure. So we can just think about how lots and lots of sentences get mapped to the truth value true. Grass is green, true. Snow is white, true. The desk is gray, true. All of these are there's multiple things in English, multiple sentences in English that are being mapped directly to this truth value. Again, that's many one. Isomorphism is one-to-one. So there's only ever a relationship between one object in the first to one object in the second. And if there was any structure in the collection, in the first one, it is preserved in the mapping. So, again, can think about something like a seating chart. You have, let's do a seating chart where, okay, we want everyone to line up alphabetically. So what we're going to do is put you in an order, alphabetical order. We're going to assign you to a seat, and we're going to assign you to seats in such a way that we don't break our alphabetical order. So it goes like, and if you follow it this way, it's going to preserve the structure that it was ordered in this manner. That's the idea of an isomorphic function. One-to-one preserves whatever underlying structure there was. Okay. So, let's quickly talk about Russell's paradox, and then I'll hit you with the last tiny bit, which is the stuff on relations. Promise. We'll be on. Russell's paradox is amazing. There's old Birdie. Russell's paradox is a problem for what's called naive set theory. Naive set theory is a set theoretic concept defined by two rules. The axiom of extensionality, which is that notion we talked about earlier, the identity criteria for sets, plus a rule about how many sets there are. So the axiom of comprehension tells us, hey, think of whatever condition you want. There's going to be a collection of things that satisfy that condition. So there's a set of all things that are tables. Cool. There's a set of all things that are non-buses. Cool. There's a set of all people who are left-handed that like Billy Joel. Cool. There's a set of people who are left-handed that like Billy Joel and the Eiffel Tower. Cool. Whatever collection you can think of, or condition you can think of, there's going to be a collection. It might be empty, in which case, cool, you've just renamed the empty set. These two axioms of comprehension and extensionality lead to a paradox. Here's the analog version of Russell's paradox. Consider a small town who has only one barber, and this barber is extremely eccentric. They follow a very strict rule. And that strict rule is that they will shave all and only those people who don't shave themselves. So again, the barber shaves anyone who doesn't shave themselves. Seems sensible. Now we ask, who shaves the barber?
Himself?
If the barber shaves himself, then he can't shave himself, because that would violate the rule.
Why?
Because he only shaves people who don't shave themselves. He can't shave himself. Because the rule says he only shaves people who don't shave themselves.
So but if he shaves himself because he's not shaving himself, then I don't.
That's the problem.
Yeah, that's the issue.
If he does shave himself, he can't. That would break the rule. And if he doesn't shave himself, then he has to, because of his rule. No matter what the barber does, something bad happens. If he shaves himself, he breaks the rule. If he doesn't shave himself, he breaks the rule. Bad stuff either way. This is the paradox.
I still don't really understand axiom of comprehension.
Good. So the thought here is basically think of whatever kind of predicate that you can. Whatever predicate you want, in English or Dutch or whatever. There's bound to be a set, according to the axiom, of things that satisfy that predicate. So, again, take the collection of things that aren't on Tilburg or aren't in Tilburg today. Cool, there's got to be a collection according to the axiom of comprehension. Take the things that are members of themselves. Cool, there's got to be a collection of those things. Take the collection of things that aren't members of themselves. Oh no. Oh no. So again, the axiom of comprehension says, think of whatever condition you can. There's a set of things that satisfy that condition.
So, is it something like likes peanut butter, and I say, well, that counts for me, my dad, and my sister. So it contains a set. So a set containing me, my dad, and my sister.
And everyone else who likes peanut butter.
Yeah, and is sane and general and still respects J.K. Rowling, like that will be an empty predicate. Okay, so okay.
Yep. Is around square. Then all set. Take it.
So I suppose the bottom problem translates to set theory in there's a set A which contains all things that do not belong to set A.
So, again, this is the analogy. Let me give it to you in the set theoretic notation. Okay? We can have a set that has itself as a member, right? So we can have the set of all sets with more than one member. That looks like it's going to be a member of itself. We can have N, which is the set of all things that aren't buses. So N should be a member of that, because it's not a bus, it's a set. Now, let's have R. R is the set of all things that are not members of themselves. This is the parallel to shaves everyone who doesn't shave themselves. So R is the set of things that aren't self-membered. Here's the problem. R cannot exist. Because, well, let's think. Is R a member of itself? If it is, then it must not be a member. Because remember, to be in this collection, you need to not be a member of yourself. So if it is a member of itself, then it's not. Oh, but if it's not, then it must be a member of... Oh, crap. So no matter what option you pick, it forces you to the other, and then the cycle repeats.
Is that the same as last week that we said God exists?
This is a similar kind of problem, right? So last week it was an issue about how could we have an empty singular term. In this case, we've set up a condition which according to the axiom of comprehension must give us a set. But when we actually follow the condition through, we cannot have that set. Because if we did, we would have a true contradiction. And that's bad. So this is Russell's paradox. It broke poor Frege's heart. R cannot exist. The axiom of comprehension must be false. Or at least naive set theory that takes the axiom of comprehension and the axiom of extensionality must be false. So, what can we do? Well, I mean, there's a couple options. Yeah, cry. That was basically Frege's response. So one thing we can do is we might try and offer something like a distinction between classes and sets. This was an initial move to make. But honestly, this doesn't help, because we can just run the same problem with whichever term you like better. Another option is you could restrict membership such that sets can't be members of themselves. This blocks the whole process right off the bat. But if you think about sets like the one I mentioned a few minutes ago, let's take the collection of all things that aren't buses. Well, that looked like it should be a self-membered set, right? Because it's a set, not a bus. So it ought to be in there. Another alternative that's very similar is to adopt what's called an iterative hierarchical approach. So the thought here is you take whatever base individuals you have. You build all the sets you can from them. That gives you the next layer. Then you build all the sets you can from the individuals and the layer that you just built. That gives you the next one. Then you build everything you can from there. That gives you the next one, and so on and so on and so on. This one effectively forces you to not have self-membership because you don't get the set until you build it. This is a kind of preferred option. And a fourth one that's really interesting, is we could just adopt a non-classical logic. That is, we could allow for there to be true contradictions. Now, a difficulty with this is we have to figure out how to make the formal system work. So much of the stuff that we did in the first half of the course relied on not allowing for this kind of thing. So this is an option, but by God, is it a lot of work. So Russell's paradox is an issue. And it's an issue for naive set theory, and it's not really clear how exactly to get out of it. Yes?
What is the difference between naive set theory and basic set theory?
Good. So, notably, when I told you basic set theory, I never mentioned the axiom of comprehension. That is the difference. I never told you how many sets there are. I gave you no principle like this that tells you how many sets can you make. I only told you a rule for identity conditions for sets and relations they can stand in. Didn't tell you anything about any comprehension schemes or how many sets we can build. So one of the big tricks here, if you want to get around Russell's paradox, is find a new version of comprehension. Find a rule that tells you how many sets there are that doesn't walk into some kind of paradox. Turns out that's real hard. Okay. Cool. So, let me stress, practically speaking, some stuff to go through, right? I want you to be familiar with some of the set theoretic notation. The basic ideas about being a member of, being a subset of. Understand how to do some of those operations: union, intersection, difference, the power set operation. And know Russell's paradox. These are the things that pragmatically we need to know from this.
No or no?
No, as in
No.
put it in your head.
Just to be clear.
Yes.
Actually study.
Yeah. Might be on the test. Hashtag might be on the test.
Allegedly.
Allegedly. Allegedly. Okay.
Is that real, that picture?
Yeah,
Really?
that's sick, huh? That's really sick. some very tight work there. Okay. So that's the stuff I really wanted to convey. That's enough for today, I think. That's enough for today. I know this is a lot. I absolutely get that. And that's totally fine, right? Again, to stress, we'll talk more about how the kinds of questions I might ask you on the final exam will look. If you've had a chance to look at the assignment, it's got some questions that look very similar to this. We'll talk about that on Friday. Don't stress about the rest of this. Don't stress about the rest of the slides or the rest of the topics. Have a read of them if you want. It's some really cool stuff, especially about the infinite sets. But that's really just for funsies, right? I was never ever going to ask you any questions about that anyway. But importantly, and I promise, I will only ask you material that's in those first two sections. From the first two sections. We won't have to talk about it. We didn't cover it here, so it'll be okay. I might mention some things about it on Friday, just again to tell you, but it won't be, it'll be supplemental. Okay, cool. So thank you guys very much for coming. Again, I know that was a lot. Before you head off, one last point. So next week, what we're going to do, next lecture, is going to continue to talk about extending our formal tools. In this case, it's going to be extending our formal tools to let us talk about things that could be or must be the case. So this is talk about modality. Please have a read of Alyssa Ney's chapter. Talks about the notion of possible worlds, possibility, and necessity. We'll go from there. Last thing. On Friday, sorry, I just remembered. On Friday, we have our visitation. So we have some people coming and kind of assessing the program. I'm part of the exam board, so I have to be there for a particular bit. This means we'll need to end our tutorial a little bit early. I'm sorry about that. I just wanted to say it. I'll make an announcement about it as well, but just to mention it now. Take care, guys. See you.
We have two lectures.